Okay, so let's get started. So project three, simple web server, is due this evening at the usual 1 second before midnight. And when you test out your web server, sometimes not all of the GIF files, the images will show. That's perfectly fine. You'd get much better performance if you implement it as a threaded web server with semaphores and mutexes, but that's not the point of this class. That would be the point of an operating systems class. And so you can imagine when the subsequent requests happen to fetch the image content, because it's not a threaded web server, it can't handle all of those requests, so it might miss a couple of those images. That's perfectly fine. When you hand it in, please make sure that you've tested it, and how you run it on your machine, please make sure that you use the loopback address 127.0.0.1 as the host name when you hand it in. Because I'm not going to have the same IP address you do when you are running it and testing it on your machine. You do not have to run the client and the server on the same machine. It's easy if you do it that way. If you run the client and the server on different machines, have fun with it. But when you submit the server in your assignment, please make sure you have the loopback address coded as the host name. And so the loopback address is 127.0.0.1. And of course, certainly, depending on which network you're connected to. So if you're connected to the network here on CIS Wi-Fi, it's going to be 10.0.something.something, right? And that's perfectly fine. And where the loopback address is different is that it's a common address that you can use to connote the fact that the server is on the same machine. Now, underneath the covers, if you're curious, when you use loopback address, it recognizes that loopback address and it doesn't even use the network card. It goes in directly through shared memory, which is faster than switching I/O for the network card. Because why use the network card if you're not physically touching the network? Excuse me, if you're not physically touching the network. And so please make sure you hand in with loopback address, and please make sure your Python web server is inside of the content directory, and your entire submission includes your write-up, your web server, all in the content directory that you've zipped up. Okay? All right. Because I will download it, I will decompress it, and I will look to run the web server and read your report and score it accordingly. Okay? All right. Any questions about this? No? And again, you can use Python 2 or 3, as I understand. Python 2 as of February is no longer being updated with maintenance releases. If you use Python 3, there are a couple minor things that have changed. The APIs are the same for socket, but as I understand, if you're using the spec about stream socket, AFINet, and all that other stuff, version 4, you use socket.afinet, not just AFINet. And so there are lots of sources online available for looking that up. Please avail yourself of them. Okay, any questions? No questions? I forgot to post that on Slack, actually. I'll do that after this. Okay, so why don't we continue on? So where we left off, we talked about TCP's design choices as it pertains to sequence numbers and acknowledgements. And we said that TCP treats a sequence number as an index into a stream of bytes describing the bytes that have been sent between the sender and receiver. And so if you're dealing with video images, you can imagine that video as being just a sequence of bytes that are concatenated together in a two-dimensional matrix to form your image. And so as these bytes come across the wire, TCP treats the ACK number as a count of which byte in that stream of bytes has been delivered. And so in this example where we left off, we have an echo application. And in this echo application, we have two hosts, host A and host B. Host A sends a single character, which is 1 byte long, to host B. Host B gets it and sends it back. And so in the forward direction from host A to B, there's a sequence number that describes the offset of bytes for this session of sending and receiving from the host from host A to host B in the forward direction. Likewise, host B also has a sequence number and an acknowledgement, and that acknowledgement is its acknowledgement or feedback back to host A to say, this is the next byte that I'm expected. I received what you sent me, and I'm sending you back the ACK to tell you what I successfully received. And it treats acknowledgements as an index into a stream of bytes. And so here in the reverse direction, we'll notice that the ACK number is one more than the sequence number for the inbound data, right? So you send sequence number 42 from A to B in the forward direction. In the reverse direction, the ACK is 43. So essentially, host B, when it says ACK 43 back to host A, it's saying, I got byte number 42. The next byte that I'm expecting is byte number 43, right? The next one in the stream of bytes. Likewise, we have a sequence number on host B, and TCP is bidirectional, and what you'll see is that host B also has a sequence number, and the sequence number connotes the stream of bytes from the perspective of host B being the sender and host A being the receiver. So from the perspective of host B, when host B sends a message in the reverse direction, it is the sender, and as the sender, it's expecting to have ACKs back from host A. So we have host B sending a response back to A, and so it has a sequence number. When it sends sequence number 79, the ACK that comes back from host A in the other direction, it has an ACK for 80. And so that's host A saying, okay, I received that character from you, 1 byte long, sequence number 79. The next one I'm expecting from you is byte number 80 in this virtual stream of bytes. Does that make sense? So we make use of both directions, and certainly in the literature, when we talked about, in the book and in the literature, when they talk about reliable data transport, they talk about it from the perspective of the sender and receiver. The sender sends with a sequence number, the receiver gives back feedback in the form of an ACK. Now, when you have two communicating endpoints, not only is host A a sender, it's also a receiver. It's a sender when it's sending information to host B, and it's a receiver when it's getting information back from host B. Likewise, host B is a receiver when it's getting information from host A, and host B is a sender when it's sending information to host A. Does that make sense? And so this sender and receiver that we talk about is a role that's played from the perspective of the underlying transport layer. And both endpoints implement the sender and receiver behaviors. Okay. Any questions about this? Does that make sense? All right, so let's continue on. And we want to look at timeouts. TCP sets timeout values. And you might wonder, how in the world does it set timeouts? Now, you might think, okay, maybe I just hard code a timeout based on what I think the delay will be in the network, but that's a recipe for failure. TCP uses active measurements of round trip time to set its timeout values that it's going to use to trigger the resend of a window's worth of packets in this pipeline data protocol that we've been talking about. And so it does that by sampling. And in the book, they call it sample RTT, sample round trip time. And each time it sends a packet and gets back the ACK for it, it's going to set a timer and measure how much time has transpired and use that as the timeout value associated with the round trip time. Now, of course, a network does statistical sharing with these packet switches, and therefore the round trip time can spike. So let's say you start using the network in the time when people are maybe eating lunch and maybe they tend to congregate on the network more, and you're going to see those round trip times increase very dramatically. It's very spiky. It rises and falls and rises and falls. And that's a very dangerous thing if you're using this timer to decide when you're going to resend, because if it swings up and down very wildly, you're going to have very bad behavior in terms of how aggressively this pipeline data protocol is going to resend n many packets in its sender window. And so it has a smoothing approach that says, okay, well, I'm going to regulate how much of my timeout value is going to come from what I currently calculated and how much is going to be influenced by new sample measurements. And so sample RTT will vary in a smooth way using this exponential weighted moving average approach. And so what this exponential weighted moving average, say that fast, what this exponential weighted moving average approach does is that it uses this quantity alpha called the mixture component. And alpha falls in the interval between 0 and 1 on the real number line. And here you'll see 1 minus alpha times the estimated round trip time, that's the smooth version, plus alpha times the sample round trip time. If alpha is closer to 0, that means that your estimated round trip time is going to be only a little bit of the current sample, but most of its value is going to be dictated by the previous estimate that you had. Conversely, if alpha is closer to 1, that means your estimate is going to depend a lot on the sample and only a little bit based on the current value. And it's called exponential weighted moving average because if you calculate this at time 0, at time 1, at time 2, well, substituting at the next time instant, the equation, it's a recurrence relation, the equation for estimated round trip time, you end up getting a successive multiplication of that first term, which is the same as exponentiating something. And so if you exponentiate a number, multiply it by itself, and that number is less than 1, much less than 1, like 0.0001, it's going to get close to 0 very quickly after a small number of multiplications of itself with itself. And so what that means is that the smaller alpha is, it's only going to count only very recent values of the sample when it's trying to determine the estimate. If alpha is large, it's going to count longer historical measurements of the sample when it's trying to determine what the estimate is. Any questions about this? Does that make sense? So if we look at this graph, on the horizontal axis, we have time in seconds. And on the vertical axis, we have the estimated, or rather the round trip time. And so the round trip time, we see two graphs. We see this blue graph, the dark blue, and that's the sampled round trip time. That's the actual round trip time from one instant to the next, measured by the TCP runtime. And the smooth version, or the estimated, is this purple version. Now, typically, alpha is 0.125, which is 1/8. So that means 7/8 of the estimate is going to be based on the previous estimate, and 1/8 of it is going to be influenced, its value influenced by the sample. And so as you increase alpha, you're going to see this purple line start to follow the sample, the blue curve, much more closely. As alpha gets smaller and smaller, you're going to see this purple line kind of smooth itself out more. And you'll notice here, well, here we see right around 15 seconds, we see a big spike in the sampled round trip time, and that influences the smooth version. It rises, but it doesn't shoot up quite as quickly, right? And the reason why you don't want this estimated round trip time to shoot up quickly is because all of a sudden your timeouts for the sender window resends is going to take much longer, right? And all of a sudden it takes much longer, and then next thing you know, the network is not as congested and things are much faster, but you're waiting to timeout, waiting too long, right? So you don't want your estimate or the value you use for the timer to vary too wildly because the conditions on the network can change very rapidly. And we see that especially here. We have a very high swing up for the sample, and then it swings really low. When it swings low, that means the network is not as congested. And all of a sudden, it swings up very high. It's very spiky. And whenever you have a spiky signal, if you're using a spiky signal to determine something like a timeout, you want to smooth out that spiky signal a little bit. And you can do that quite dramatically with the estimate using this alpha smoothing, exponential weighted moving average. Any questions about this? And in fact, this is a technique from general field of study called time series analysis. This is used for stocks, for all sorts of things, to try to smooth out spiky or jagged signals. Okay, any questions? No? All right, so there's a timeout. Now this simple timeout isn't used directly. The timeout plus some standard deviation or some notion of dispersion is also used. And so a similar technique, this exponential weighted moving average, is used with a deviation, and the actual timeout value is usually set based on the sample estimate plus some deviation or some multiplier times the deviation. So here, instead of alpha, we use beta because we need a different coefficient. And this beta smoothing is used to shunt, if you will, the contribution of the current deviation. And so the current deviation is based on the sample. So we have the current sample minus the estimate. That's how much the sample differs from the smooth version. And then we're going to count that some beta amount. And then 1 minus beta is the deviation of the round trip time. And so that's the smooth version. And this beta, a good value for it is 0.25. So that means 75% of the time, the deviation is going to be from the previous deviation estimate, and 25% of that value is going to be from the current deviation. Okay? Are any questions about this? And in fact, this is something you can actually see using some of the extended Wireshark tools. And so the timeout interval that is typically used is your estimate plus some safety margin, some integer multiplier, positive integer multiplier times the deviation. Does that make sense? Any questions? So that's how the timeout is set. It's set from live measurements that are smooth using exponential weighted moving average over real samples. And the sender TCP runtime can take those because it sends, it knows when it sent, and it also knows when it got back the acknowledgement. Okay, so let's take a look at more of the implementation details of TCP, Transmission Control Protocol. So it's pipelined. Okay, it uses something like go back n, right? So it's pipelined and it has cumulative ACKS, and therefore it has a single retransmission timer. And that retransmission timer is associated with the oldest unacknowledged in-flight packet, right? So that would be the smallest byte in that sequence of bytes represented by that window on the sender side. You have a single timer, and there are different things that can trigger a timeout, a resend. You can have a timeout event, so that timer expires, so it assumes that data, that packet was lost, or it has a shortcut, and the shortcut is triggered by duplicate ACKS, and we'll see later specifically triple duplicate ACKS. And the reason for that has to do with this timer, right? So the timer is some estimate plus a deviation. But sometimes you want a shortcut because you can infer other types of information about the network. When your routers start to get congested, right, they start to fill up and they're slow to store and forward a packet. Now, what happens when you're slow to store and forward a packet? Well, it's taking long, and that means the ACK is going to take long to get back. But the network isn't to a point where it's catastrophic. And so when the network is starting to slow down, it'd be nice to be able to do something ahead of time rather than waiting till the catastrophic event all the way when this timer expires. And so what TCP does, it says, okay, well, I know I'm sending a window of packets, right, more than just one segment at a time. And so if there's some loss, whether it's an ACK or packet, I'm going to get multiple ACKs because I'm sending more than one packet. Right? And so if I get duplicate ACKS, 3 of them specifically, well, there must be a condition where I'm on a bad trajectory in the path from between the sender and receiver endpoint. It's approaching a condition where it's starting to get congested. And so this is a shortcut that says, let's not wait until the timeout expires. Let's ahead of time shortcut and trigger a resend. And so in TCP, retransmissions of the sender window worth of data is triggered by the timeout. That always happens in RDT 3.0 using pipelining and go back N approach. But TCP also has this duplicate ACK that it tracks. And if you get 3 ACKs in a row, boom, 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 ACK, 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 and it's the same ACK, like ACK 100, ACK 100, ACK 100, it'll trigger a resend. Okay? All right. Any questions about this? All right. So we also will, in this case, it's going to simplify TCP a little bit for the sake of writing the finite state machine to describe the detailed behavior. And so for this next state machine, we're going to ignore the duplicate ACKS, and we're also going to ignore flow control and congestion control for now, right? Okay, because we're not done yet. All right, so you have data that's received from an application layer above received by the transport layer, and you create a segment with a sequence number where that sequence number represents the offset into a stream of bytes. And you start a timer if there's one not already running. And you think of the timer as being for the oldest unacknowledged segment because it's go back end style pipelining. And so that timer is associated with the oldest packet or the smallest byte offset. You set your timeout interval based on that interval that was measured using that exponential weighted moving average plus the deviation that we talked about. And then if you get a timeout, you retransmit a segment that caused the timeout, restart the timer. If you get an ACK, well, the ACK acknowledges previously unacknowledged packets, and since it's cumulative, if you get an ACK for a later packet, you can assume that all the packets before it were successfully received. Okay, so let's take a look at the finite state machine for the TCP sender, and this is simplified. You start out with a sequence number and a send base, or send base was that sequence number associated with the left-hand most or the oldest packet in the sender window. And we start out, we're waiting for some event to occur. So let's take that top edge, the decoration on that, on the transition. You receive data from the application layer above, so someone calls RDT send. You create a segment, and you give it a sequence number, and that sequence number is set by that variable next sequence num. So now you do a UDT send, so TCP passes that segment to IP, Internet Protocol, right? We're talking about TCP details here. And then you set the next expected sequence number to be the current sequence number that you just stamped on the packet and send, plus the length of the data that you sent. And so that's where this idea of sequence numbers points out the idea of sequence numbers as being offset into a stream of bytes. So if your segment that you sent out has 100 bytes in it, next sequence num is going to be 100 more than what it used to be after you did the UDT send. Does that make sense? And any questions about this? And this is TCP details. All right, so then you start a timer if it's not already running, and you can have a timeout event. If you have that timeout event, you retransmit all of those unacknowledged segments for which the sequence numbers have not been acknowledged. You resend everything in the window, and then you restart the timer. If you receive an acknowledgement, well, you look at the ACK number, and if the byte offset associated with acknowledgement is greater than what you have received before, it's cumulative ACKs, so you can assume everything before it was also acknowledged. So if you get an ACK with some value y, if it's greater than the send base, then you update the base of the sender window, and that's sliding that window to the right, and now you have available more sequence numbers that you can use to stamp outbound segments. Does that make sense? Any questions about this? Okay, so let's take a look at some examples, and these are simple examples. We have host A on the left, host B on the right, and let's take a look at the first scenario where the acknowledgement was lost. The time increase is going down the board. So we start out, host A sends a message 8 bytes long, and the sequence number is currently 92. So offset 92 in that virtual stream of bytes. So it sends that data, it arrives at host B, and host B then says, okay, next sequence number is equal to the current sequence number 92 plus the length of the data that was sent. So 92 plus 8 is 100, so it sends back an ACK with 100. And when it sends back the ACK of 100, it's saying, okay, I got your data, and the next sequence number I'm expecting is sequence number 100, corresponding to position 100 in that stream of bytes that you're sending to me, piece by piece. So let's assume that that ACK was lost. If the ACK was lost from the perspective of host A, it sends 8 bytes starting at sequence number or offset 92, and then it doesn't hear back. So eventually that timer fires if it doesn't hear back, and what does it do? It resends. So it resends that message starting at offset 92 or sequence number 92. It sends that 8 bytes again. It buffers it on the sender side after it did the original send, and then that makes it through again. Now that's a duplicate segment that is received by host B. Host B has already received it. So what does host B do? Host B does not deliver it, just throws it away, but it resends the ACK that it most recently sent. So it sends once again ACK 100. Does that make sense? All right, any questions about this? So that's the case where we lost the ACK. Let's take a look at what happens with a premature timeout. Premature in the sense that the timeout expired before it received the acknowledgement. So we send two packets back to back because it's a sender window on host A. And we send, again, 8 bytes starting at sequence number 92. So the corresponding ACK, next sequence number, is 92 plus 8. That's 100. Then, once we send that 8 bytes starting at sequence number 92, we get another message sent at host A, and we send, starting at sequence number 100, 20 bytes. 20 plus 100 is 120, so the ACK that should be associated with that is ACK 120. So we have two packets in flight, 8 bytes starting at sequence number 92, and 20 bytes starting at sequence number 100. And so we get the first segment at host B. It sends back ACK 100, right? That's next sequence number, 92 plus 8 is 100. And then it gets sequence number 100. So host B already knows ACK 100, so the next thing it should be receiving is something with sequence number 100. So it delivers that data starting at sequence number 92, and then next sequence number it's expecting to get is sequence 100. So sequence number 100 comes in because it's sent back to back as a sender window, and so the receiver gets it and says, this is in order. It delivers it to the application layer above, sends the ACK for sequence number 120. Okay, so now at that juncture, ACK 100 and ACK 120 are both in flight. But let's say they're taking a really long time to get there in the reverse path back to host A. So what happens? That timeout fires. Whatever value that estimated round trip time plus the deviation was, that timeout expires. And what does that host do? It gets ready to now send it. So that timeout expired, and what expired is associated with the oldest unacknowledged packet. So the oldest unacknowledged packet was that first message or segment starting at sequence number 92. So the timeout expires before these ACKs can come in. So what does it do? It resends that oldest unacknowledged packet, and that's those 8 bytes starting at sequence number 92. So now, in the meantime, that resend of that first segment, it's in flight in the direction of the forward path from host A to host B, and then in the meantime, it gets ACK 100 and it gets ACK 120. Now, at this point, we got ACK 100 says, okay, the receiver has given me feedback saying it's received those 8 bytes, and then ACK 120, the receiver is giving me feedback saying it received those next 20 bytes starting at sequence 100. So now, this sequence 92 that was the result of the resend due to the timer expiring, that's a duplicate send. Now, of course, at that moment, the receiver says, well, I got sequence number 92, but I just told it most recently I'm expecting sequence number 120. So it throws that away. It's an out of order segment, out of order packet. So it throws it away, does not deliver it, and it sends that ACK again saying, hey, you sent me something out of order. I need sequence number 120. And this continues. Okay. Any questions about this? All right. Let me do a time check. Okay, 12:54. So let's take another scenario. This is the cumulative ACK. If an ACK is lost and another ACK comes in, and that ACK that comes in has a bigger sequence number further in the stream of bytes, because it's cumulative ACK, the receive sender just assumes everything up to it was delivered. So let's take a look at that scenario. So again, we send the first segment starting at sequence number 92. We send 8 bytes worth of data. And so we also then send another 20 bytes starting at sequence number 100. So we get the first segment at the receiver, and our next sequence number is ACK 100. So that's the next sequence number it's expecting from the sender. It also then sends ACK 120. So in the case of the first segment received, host B received it, it's in order, it delivers it to the application layer above, it sends ACK 100, and then it gets sequence number 100, says, hey, this is in order, I'm going to deliver it to the application layer above, and it sends ACK 120. But in the meantime, it sent ACK 100, and ACK 100 was lost for whatever reason. Maybe there was some congestion or what have you on the routers. That acknowledgement was lost on the reverse path from host B as feedback going back to host A. So it was lost, but ACK 120, which is right after it, made its way through. So from the perspective of the sender, well, it sent sequence number 92, sequence number 100, and now it's just waiting. And all of a sudden, it got sequence an ACK for 120. Now, the sender knows that it sent sequence number 92. It knows it sent sequence 100. and all it sees back from the receiver is ACK 120. But it knows that the receiver would not have sent ACK 120 if it didn't already have sequence number 100, right? The one that came before it, rather 92, the one that came before it. Because it knows 92 plus 8 is 100, 100 plus 20 is 120, right? And because ACKs are cumulative, it gave the ACK of an offset in this byte stream that comes later, so everything before it must have been successfully received, because the receiver would not have sent ACK 120 if it did not successfully receive that first segment and send ACK of 100. And that's because of cumulative ACKs. Okay. Any questions about this? Does that make sense? Okay. So I'm not going to exhaustively read this table. It's in the book. I'll let you read it. It enumerates what actions the receiver takes given certain events. If something arrives in order, you deliver it and you send the ACK based on the payload size. If you have something out of order, you ignore it and you resend the ACK for the thing you're expecting next. Okay? All right. So let's take a look at this idea of so-called fast retransmit. This fast retransmit is a condition where it detects duplicate ACKs. And the fact that you're doing pipelining, because the sender sends more than one packet back to back to back, if you have something that's missing or something gets dropped, you're going to end up with duplicates of the same ACK, right? Because if you are expecting a certain packet and you don't get it, and you get 3 out of order packets, you're going to send an ACK 3 times, a triple duplicate ACK. And so the timeout period is typically very long, and so there needs to be a way to kind of speed up its response on the resend under various conditions. And again, you don't have to wait or shouldn't wait until the absolute worst case, and that's there's no packet gets sent at all. You have the extreme congestion. If you're approaching congestion, you want this thing to be able to react much faster than waiting for the timeout to fire. So if you detect lost segments, that's done. Another way of doing it is by checking for duplicate acknowledgments. If a segment is lost, then most likely they're going to be more than one ACK by the nature, because this is a pipeline protocol, you're going to have back-to-back-to-back ACKs. So TCP in its implementation does something that's called fast retransmit. If it receives 3 acknowledgments for the same data, so-called triple duplicate ACKs, it resends that segment with the smallest sequence number. Okay? All right, any questions about this? I think my next slide is a bunch of schematics. So here's an example of this triple duplicate ACK. So we have a window on the sender side, and that means we're going to send more than one segment. And in this case, again, because it's TCP, the sequence number is an offset in a virtual stream of bytes. So we send sequence number 92, 8 bytes of data, and then we send at sequence number 100, 20 bytes of data. And it doesn't matter what the next 3 are. We just send back to back to back some more segments because we have the space in the sender window, right, for additional segments. So we start out, let's say the first segment is received, sequence number 92, 8 bytes of data. So you ACK 100 because 92 plus 8. The next offset is going to be at position 100. So we send back ACK 100, and for the sake of example, the next segment, starting at sequence number 100, that gets lost. We still sent the additional 3 because we have that many positions in the sender window. But now what happens, we get this first segment on host B side, the receiver. It sends ACK 100. So the next segment it's expecting should have a sequence number of 100. Sequence number 100 was lost, and then we sent the next sequence number after that, next one, and next one. So in response to those last 3 segments that are sent, it says, well, I was expecting sequence number 100. That's out of order. I was expecting sequence number 100. I was expecting sequence number 100. So it sends these 3 ACK 100s. That's a triple duplicate ACK. It sends a duplicate 3 times. The same acknowledgement was received. So on the sender side, it gets that first ACK 100. Okay. And then time transpires between that and when it gets those 3 ACKs in rapid succession. ACK 100, ACK 100, ACK 100. So it uses that event, the triple duplicate ACK for ACK 100, to trigger the resending of the oldest unacknowledged packet, which, by the way, had sequence number 100. Okay? And after that, it moves forward instead of waiting for the timeout to expire. Does that make sense? And so this triple duplicate ACK speeds up the responsiveness of the sender, saving it from having to wait for the timeout period if it detects that the conditions on the network were starting to degrade. Okay? Are any questions about this? All right. So let's take a look at this next concept. We'll probably end with this concept, flow control. And this diagram does two things. It presents to you which aspects of the internet stack are implemented in the operating system versus the application layer, but it also looks at the buffer and the relationship between inbound data to the transport layer and outbound data. So here we have in the application space for the operating system, your usual application processes that are running. And then here we have within the operating system the runtime for TCP, the TCP runtime, implementing the TCP transport layer protocol, and the runtime for IP, implementing the network layer protocol. So we have from the sender, we have data coming in, right? Data comes in from the link layer, the physical layer to the link layer, and then makes its way into the network layer, and from the network layer strips off its header and gives a segment into the transport layer. So that's your inbound data. It's a segment. So the segment, of course, is slower than TCP is in delivering messages to the application. And the reason why it's slower is because they might arrive out of order. If they arrive out of order, you have to wait for the in-order packets. But in the meantime, the application above, it just wants that data, right? If it's video streaming, it wants that data. Audio streaming, whatever it is, it doesn't matter. It wants that data as fast as it comes in. But the transport layer has to slow down because it might not have things ready in order, and it has to assemble them in order. So for that reason, that the data coming into the receiver buffer is arriving slower than, or more slowly than, the application that wants to get that data delivered through the socket interface. Okay? And so what happens then is that sometimes the sender can speed up or slow down, and when it speeds up and slows down, everything must be delivered to the application through this receiver buffer. Well, something can happen. What happens if your receiver buffer runs out of space? Then you're done, right? You have to drop some data. And you don't want to drop that data if it took so much effort to check the checksum. Is it an ACK? Is it triple duplicate ACK? What's the sequence number? That's a lot of work to do just to result in throwing it away because you ran out of space. And so what this flow control does, it says, okay, well, the receiver endpoint in TCP, it knows how much free buffer space it has. It has a window size n, and it knows how many bytes worth of data it has left to store. And so with flow control, the receiver is going to send data back to the sender in the acknowledgement packet that has information about how much available buffer space there is in the receiver. And that is called flow control because in response to getting that buffer space, that free buffer space information, the sender is going to say, if my receiver endpoint that I'm talking to, sending data to, if it can only store a certain amount of data, it's useless for me to send more than is available to be stored on the receiver side, because all segment data must be buffered at the receiver buffer in order to deliver it to the application. So if you only have 20 bytes left of storage and someone sends you 100 bytes, you're going to have to throw it away. It's just all that effort wasted. So if you only have 20 bytes left of storage, the sender is going to say, oh, the receiver just told me in the ACK that there's only 20 bytes available. So I'm going to change the size of my sender window to match the amount of available buffer space on the receiver. Does that make sense? Any questions about this? So this is called flow control. And in flow control, the receiver is going to control the sender window size so that the sender will not overflow the receiver's buffer. And it'll overflow the receiver's buffer if it sends more data, i.e. its pipeline, its sender window is so big that the data received is more than the amount of buffer space on the receiver. Okay, so on the receiver, it has a buffer, and the receiver buffer has some size, and the data is pulled out of that buffer and is depicted here as being the top of the buffer, but it doesn't have to be the top, at a certain rate. And There's empty space called the free buffer space, and the variable or the name used in the book is called the receiver window, rwind. And rwind is a count that says the number of bytes that are available in the receiver window. And so the receiver so-called advertises rwind to the sender by stuffing this rwind count in the packet that it sends back across the wire to the sender. And this guarantees that the sender will not overwhelm or overflow the buffer space in the receiver. So this is not in the slide deck that you have. I just kind of did it again so that I wouldn't have to go backwards like 10 or 20 slides. But in the TCP segment structure, we have, as part of the TCP header, this thing called the receive window. And the receive window is a 16-bit number, so you can have up to 65535 many bytes as the buffer size advertised or sent back to the sender. And when the sender gets this, it sees receive window and it says, there's only this much space left in the receiver's buffer. Let me cut the size of my sender window so that I won't send it faster than it can be stored. Does that make sense? Any questions about this? No? All right. So it is now 1:07, and I'm in between many of your spring breaks. So I'll cut it a little bit short. Now, let me not start a new module. Let me cut it short now and just stop there. So that's all I had for today. We will end there, and we'll finish this up when we get back from the break.